simplest possible way you can introduce defects. You know, just put it in the furnace, take it to 1200 degrees Celsius or something. That will introduce defects. Well, good point that for most of the ceramic material, you will have to go to very high temperature, which has a thermal cost. So thermal energy cost, you might say, okay, from going to 1200 or going to 1500, I don't have a furnace. What are you going to do next? You can say, I'm going to dope into it. For doping, you will need 10%, but not as high as creating Schottky defect. So, you can dope. And depending on the amount you can create certain amount. So you already know about those two ways of introducing defects. One is the so-called thermal energy. Thermal. The other way is that you can do doping. So this will be intrinsic defect, like a Schottky defect or Frankel defect. Or you can dope and create so-called extrinsic defect. So this is like adding impurity. So when you add impurity in the second phase, there's always a possibility that you may be incorporating a second phase in the material as well. There's always a risk that you may not be able to dissolve it completely. So in a way, if you don't dissolve it completely, then you will sort of contaminate your sample. Okay? So is there another way of, much cleaner way of introducing point defects? And that is what I'm going to talk about today, so-called environmental control. So for example, you can take your oxide, put it inside a furnace at some elevated temperature, not as high as needed for Schottky defect, and control the PO2. And that will lead to the so-called controlled atmosphere processing that I wanted to talk about as a topic. Controlled atmosphere process. So you will see that you can control the environment, something like offset pressure, and introduce point defects. If you compare between 2 and 3, there's less risk because you are not introducing any impurity. But in the doping, depending on what you are putting in, you can always create a second phase or your impurity will do weird things that you don't want. So this is a much cleaner way of introducing point defect that leads to the topic today, into the so-called non-strike inventory and so on. And I will eventually get to program ring diagram that will be sort of the point defect stability that way from the solutions. So you know that, if you take oxide for red as an example, then you can realize the metal deficient. Metal deficient oxide, like you start with an FeO oxide, which is an insulator. Good point. Thank you. Good. All right. So if you introduce some non-strike mechanism, cation substance. Then you will convert this insulator into a semiconductor. So there are materials like iron oxide, cobalt oxide, nickel oxide, and a few others that will create non-stoichiometry on the metal surface. And it's done by control of PO2, which is kind of not increasing. You might think the PO2 will affect the anion synthesis, but there are some oxide where because of the bonding and interaction with the cation and anion, the preference will be PO2 that will be actually, well, in a way you can think of this as excess oxygen relativity or metal deficiency. There are other oxides like iron or cerium oxide and so on, where you can create the deficiency on the oxygen. So in this case, you will be creating vacancy on the iron surface. In this case, you will be creating vacancy on the oxygen. And you will see that you are creating vacancies that you could create either by thermal energy or by local. But instead, you are creating this by controlled environment. That's a cleaner way of doing it. And you can always do this experiment relatively easy in a lab. Question is, how do you control the pure net? Why? Talk about that as well. So, you can look at this metal deficient oxides. If you think about the scenario in terms of the point defect thermodynamics, what you're doing is your iron oxide is interacting with the gas environment. You can see this oxygen sitting on the oxygen lattice in the solid, in iron oxide. And depending on the PO2, it's going to create deficiency on the iron sublattice. The deficiency is presented in terms of vacancy on the iron. Okay. So you change PO2, that will change the number of iron vacancies, or that quantity X that you can actually change. You can control that X very given. And then this is compensated by 2 holes. And this 2 holes will what they will do is that you non-stoichiometric iron oxide. Now you can see that since it is iron 1 minus XO, all the iron cannot be divalent anymore. Right? So if I have talked about this a little bit before. So if in your FeO, all the iron are divalent. But when you convert this into a non-stoichiometric Fe1 minus XO, you can see immediately that all the iron here cannot be divalent anymore. Some of them will have to be trivalent. So you will have a mixture of mostly divalent, but there will be some trivalent. And you immediately think that, okay, if I have iron oxide now with both the divalent and trivalent, I can get electron hole. So unlike this material, which is an insulator, this becomes a semiconductor. And you can see the mechanism of formation of the iron P plus with this hole that you need to compensate for the charge will convert to a divalent iron into trivalent. Okay? And if you want to, let me show you the cartoon first. So you have your iron, oxygen. This is my cartoon for iron oxide. So you can see that iron is missing here. So vacancy of iron site. And as a result of that, for creation of 1 iron vacancy, 2 of the divalent iron will convert into trivalent. So this iron or iron site, 1 positive charge is trivalent iron. Okay. So you can look at this from a band diagram perspective as well. So I go back to whiteboard. Okay, so think about your band diagram. So you have conduction band and valence band. And your ion vacancies that you are creating, those are defects pointing that they will lie in the band gap region close to the top of the valence band. So they will act like an acceptor type energy states. And with a little bit of energy, they can extract electrons from the valence band and becomes too negative and creating two holes in the valence band. So you know, in semiconductor, people who don't accept doping and donor doping, you're not putting it empirically, but this is a way of, by controlling the PO2, created some ion vacancies. Now they are acting like an acceptor state. And now you can see the material doesn't have to conduct by exciting electron across the entire band. With a little bit of energy, you can create holes and it will become a p-type semiconductor. So this material that was an insulator, when you create Fe1 minus X hole, the non-stoichiometric one, becomes a p-type semiconductor. And so this is band diagrams. Look at this kind of phenomenon. Similarly, in the other material, like the so-called oxygen deficient that I'll discuss on the next slide, here's an example of FeO. You can see this is the phase diagram of iron to the left. And as you move to the right, you're adding more and more oxygen. So this iron-oxygen binary phase diagram. And you can see this is the Bush-type phase stability range. And there's a huge oxygen non-stoichiometry or oxygen tension, rich oxygen PO, that you can control to create different levels of Fe1 minus X. So you can see that range is, depending on the temperature, the higher the temperature, the range is big. So there's quite a bit of window. You can tune your X simply, and the tuning knobs your PO2. Do you have any idea how to control PO2 in the lab? So you say, okay, this is your FeO, take it to the lab and go create X, let's say this example. This one is 5% vacant site on iron sometimes. You can see that X is 0.05. Okay. You can create this material at 1200 degrees C by controlling pressure roughly in this range. You will eventually have to tune the exact pressure. There's a way to control the exact PO2 in the lab that we'll talk about. And here's some data. You can see that if you create different levels of non-stoichiometry, so as you move from the bottom to the top, you're creating more and more iron vacancies. You can see there's the effect of the lattice spur. As you create more and more vacancies, the lattice will collapse a little. The lattice parameter will change. You can see that change in lattice parameter. You can pick this up in X-ray diffraction, for example. talked about this last time. So your X-ray diffraction peak will shift accordingly, and you can see the effect on the density of the materials. So density will be going down as you introduce more and more vacancies. So people actually do this on a regular basis, instead of measurements. And, we'll talk about these other types of non-stoichiometry. So the next one is the oxygen sublattice non-stoichiometry. Looking at the point defect thermodynamics, in this case, the opposite will happen because it's creating vacancy on the oxygen sublattice. Things like TiO2, ZrO2, cerium oxide, etc. So in this case, oxygen sitting on an oxygen site in the lattice, in your TiO2, will be interacting with the environment, so it will actually leave the lattice to create oxygen vacancy, and it will become half a molecule of oxygen gas phase, and it's just compensated by electron. Okay, so this will become an intensity study, and this electron will actually convert. Very similar picture that in TiO2, all the titanium are tetrahedral, but in TiO2 minus Y-rays, some of them will have to be trivalent. And now you can see when you have a picture of titanium 4 plus and titanium 3 plus, it becomes a semiconductor. In this case, titanium. You can see the picture, cartoon picture here again, with titanium and oxygen. And you can see that here's an oxygen vacancy. Because of this oxygen vacancy that you create by controlling VO2, the effect will be that titanium on a titanium site, some of those will have to become titanium 3 plus. The rest are still titanium 4 plus. So this is the effect, and if you want to look the band diagram picture, it will be just the opposite. See, can I erase partially? Okay, so it becomes like maybe it was easier to redraw than erase it. Okay, so the effect is different or opposite in the sense that the vacancy on the oxygen site will create donor states in the band. And with a little bit of energy, it will donate electron to the conduction band and become too positive. So unlike in the other material, this is creating the vacancy that is created by environmental control is acting like a donor state that in semiconductors people usually create by putting donor type impurity. So this is much more effective. Obviously, we are doing this in an oxide. This is large band gap semiconductor. Not as good as in silicon and germanium, but if you can replicate a large band gap semiconductor, then this is a much better way of increasing quantity. So you don't have any, you don't have to worry about contaminating the second. Okay? All right. So that's what this is all about, and electroceramics community all the time. Okay, I have a question before I move on to programming like that. And I'm trying to come to an answer. In fact, if I give you a material, it will know nothing about. Absolutely. You can sit down at home and you can construct this programming diagram for your material just based on the dimension. But then, how good is the diagram? You will have to see. You can do some experiment and verify whether the diagram constructed realistic diagram. So let me tell you how to construct the diagram. I'm going to start an example where you know something. So that is easy. If you didn't know all of these facts, it would be more difficult in the sense that you have to create more detail, more possibilities, more equations, more calculations. But this is, we're talking about a non-material MO, it's a divalent M, and it says that it contains predominantly oxidant vacancies. Predominantly oxidant vacancies at low pH, which is typical of an oxidant. If you go to very low pH, it will have oxidant vacancy. On the other hand, if you go to very high pressure, it will have oxidant interstitial as the dominant. So these are some known facts. And then it says in the intermediate region, the oxide is stoichiometric, which is here, where you can get conduction only by performing intrinsic excitation across the band. It is stoichiometric. Or it may have anti-Frankel condition, which is not very likely scenario. Remember, we talked about this. It's very difficult to define an. But nonetheless, this is a thought process. It's given me some facts about them for you. And it says, for the sake of simplicity, assume the defects to be doubly ionic. What does that mean? You can probably say, okay, see that? This oxidant vacancy is doubly ionized. And depending on the temperature and PO2, possibility of having neutral oxidant vacancy, neutral, singly ionized, or fully ionized, that is double ionized. These are the possibilities. And in fact, under certain conditions, if you create oxidant vacancy that are neutral, there will be very deep level in the band head. Much deeper level. Meaning that it's going to be very difficult. It requires a lot of energy to ionize, to donate one element. So it will prefer to remain neutral. Or, under certain conditions, you may create singly ionized and the energy level will be less deep. So instead of donating 2 electrons, it will donate 1 electron and become singly ionized. Or we have the other possibility. So you can see that if you knew nothing about this system, you have to include all the possibilities. So your math becomes, you have to deal with more equations. That's it. But the general calculation procedure will be similar, with just more equations to do. So this is why simplify the problem says that assume that the defects are doubly ionized. So forget about neutral vacancies, singly ionized. So we go through the calculation, you can see that first step is writing the defect equilibrium reactions. So these are the possible reactions at low PO2 dominated by oxidant vacancy, at high PO2 dominated by oxidant interstitial, and at intermediate PO2, there are 2 possibilities: intrinsic excitation across the band gap, or anti-Frankel defect. That's anti-Frankel. And associate each of these reactions, these are the equilibrium constants. So that's step number 1. What was step number 2? Right. You shouldn't know this. Associated with each chemical reaction, write the equilibrium constant. And you will see that on the next slide. So associated with each of those reactions, if this is the equilibrium constant, comes out of this form, you can see that VO2 is coming from the reaction. This is, whenever you have a gas species, activity becomes equal to pressure. Okay. So while this becomes fractional concentration, this will become VO2. So that's why we see VO2 in the functions. So this is associated with the second one, the third one, and the fourth one, entry cycle. So that's step number 2. What was step number 3? Electron-neutrality condition. So electron-neutrality condition is simply you're putting on the negative charges on the left hand side and equating to the positive side. So this is the overall electron-neutrality. What was the step number 4? Solve it using this electron-neutrality condition. Go back to this equation and solve for each of the defect concentrations. You can see that this, going through these 4 steps of conversion calculation is relevant in constructing this over time. But there is a trick that you can, unless you are a brilliant mathematician, you can simplify the electron-neutrality condition for each of these regions. Remember, we're dealing with low PO2, intermediate PO2, and high PO2. You can go and say, okay, at low PO2, I know that oxygen vapours is going to dominate for our oxygen interstitial. We can ignore oxygen interstitial, and associated with oxygen interstitial, you have electron holes. We ignore this and ignore that. The electron-neutrality condition becomes much simpler. Use this electron-neutrality condition, go back to each of this equation, and solve by eliminating it. You can clearly see that the first equation, you have 2 unknowns, oxygen vacancy and electron concentration, and electron-neutrality condition will help you eliminate all of this and will allow you to solve. And you can do that going through each of these, and the solution will give you that oxygen vacancy concentration will change in a very, very predictable manner. You go to the 2 region, and as you change your condition in that region, your oxygen vacancy concentration will go down. This PO2 to the exponent of negative 1/6. Very predictable. Decrease your PO2 10%, you know exactly how much the oxygen vacancy concentration will be. That's the beauty of this thermodynamics, is that it gives you, and by the PO2 is your experimental control. That's what you're controlling here. And you're getting predictable defect concentration in your experiment controlled way. There is no other beauty like this. Okay? And you can go to oxygen interstitial, will go as PO2 with the exponent plus 1/6. 4 will be PO2 plus 1/6 and so on. Then you can go and say, I'm now going to solve for the high PO2. Very similarly, the high PO2 oxygen interstitial will be dominant here. So you simplify the electron-neutrality condition and solve. In this case, you will still get 1/6 type PO2. Then you go to the intermediate range, 2 possibilities. Intrinsic ionization. In the central defect, you can say in intrinsic ionization, electron and hole concentration will remain flat. Even if you are changing PO2, their concentration will not shift. For oxygen vacancy concentration will go down as 1/2 to exponent 1/2. So exponent changing. And then the cycle will have different effect to 1/4. And again, you are making predictable defect concentration in different regions. And before you construct the proper weight diagram, you can summarize your defect concentration, and you can indicate in each of these regions, this is low PO2, this is high PO2, this is the intermediate with two possibilities. And you can just list the exponent of the PO2. And then you can, if you know the equilibrium cost and balance, how do you find out equilibrium cost and balance? The thermodynamic calculation. You have to know the delta G naught the react. So that is given to you, you can calculate equilibrium cost. So then you can construct the phase diagram. So this is the phase diagram in differential machines. And this is the intrinsic ionization. You can see that at low PO2 oxygen vacancy is dominated to the exponent of PO2 to the negative 1/6. And then if an differential defect model, you get a flat region, the intermediate range, where the conduction is going to be dominated by ionic species. So once in this PO2 range, your material will be an n-type semiconductor. In the intermediate range, your material introduced an effect of defect in ionic. Because you can see that electron and hole concentration is much lower than the ionic type species. But on the end, then eventually in the high PO2, it will become a p-type. So in this case, if you look at electrical conductivity of the material, it will look like something like this. In fact, so if you look at the logarithm of electrical conductivity as a function of logarithm of PO2. Typically, this axis is taken as LOG, logarithm to the base n. Do you know why? This axis is typically LOG PO2 and not natural log. Because PO2 is typically reported as exponent of 10. It is that PO2 is something like 10 to the negative 8 most. So because of that, it's typically log. Anyway, so this material with n-differential defect will behave like n-type, and it will go through an ionic and then move on to p-type. This is interesting. It's saying that if you expose your material in this range, okay, all right. Then it will be an ionic. But if you operate this material in this range, it will be an n-type solution, and so on. Similarly, in this range, very high PO2, it will act like a p-type solution. Very important things to know about your material. Don't you agree? Okay. All right. On the other hand, for the other possibility, the intrinsic ionization, like metal or metal oxide, you can see that it's going to go from n-type and it will keep on doing a mixture of N and P electronic and then eventually p-type. So it is never going to go through the ionic, So if you don't have any type of defect in your material, you can just look up any type B. Okay, so now I'm going to speak a lot of the other calculations you can do this for, materials that you can control the point defects by metal paper. Something like your halogens and so on, chlorides or bromides and those kind of material. You can control the chlorine pressure in the environment, bromine pressure, etc. and make a crucial calculation. I'm going to not bore you, but you can just see that it's going through step number 1, that's equilibrium constant, step number 2, the electroneutrality condition you see there, and then there's using this electroneutrality condition, and in this case, at low metal pressure, it's dominated by P-type behavior. At high metal pressure, N-type behavior. And then in intermediate range, it can be higher, right, than that yet. So you can create this kind of, construct this kind of diagram. I'm going to show you some calculations from Lawrence White's book. I have given you that reference. You can see that this is, again, log of electrical conductivity versus CO2. You can see the material is strong and tight of it. It's very important for our electric material. It's going from a low CO2 N-type semiconductor to P-type semiconductor. It doesn't have this ionic flat region. And it's interestingly at low temperature, so this is 800 degrees Celsius, the CO2 exponent is -1/4. Our calculation predicted -1/6, which happens at high temperature. You can see that 1000-degree data looks more like -1/6. But low temperature data, -1/4. This is what I call, if you have possibility of creating WRs possibilities, you're doing that, you get -1/6. -1/4 comes from single ionized digits. So again, at low temperature and similar CO2 ranges, the defects will be created by single ionized ion efficiency, which is because that oxygen vacancy is now sitting a little deeper into the bed of the bed. It can only be excited singly. So these are details that, similar kind of diagrams or various taken that from the ferroelectric material, again going from N-type to P-type. And again, you can see that this is 1/4, and this is actually 1/6 at high temperatures. This is potassium tantalate, another important technology. Again, used from N-type to P-type. So none of these materials have this ionic type defects in there, in the sense that they keep the ion. This is the program big diagram for similar zirconia that we talked. And remember that's an important technological material because it's used in oxygen sensor, high temperature fuel cell, oxygen pump. It's an interesting material. If you take a strip of stabilized zirconia, dense, density should be in excess of 90% or 95%. And then if you apply electric field voltage across the thickness of that membrane, you can pump oxygen from outside to apply voltage. You increase the voltage, more oxygen. And in fact, in a lot of medical technology, oxygen pump based on decreased circular zirconia or gases Okay, so you can see the proper V diagram. How basic this looks. See how many regions? Lowest CO2, then a little bit higher. Still low. Then some intermediate, moving into the high and so 1, 2, 3, 4, 5. If you remember the theoretical term, if you didn't know anything about this, you would assume all this possibilities. Remember, I said singly ion, doubly ion. So that will increase your CO2 control ranges. Because experimental control is superior and temperature. So this is why it shows all this possibilities. But you can see that oxygen vacancy is dominating here. Then it's decreasing, and this is dominating this intermediate range. So you will get some mixed effect here. So this is N-type, mixed. And then this is ionic, completely. And then when you get mixed, ionic P-type, and eventually. So based on this defect EMN, Kruger-Fink diagram, you can predict how the electrical conduct works. It says N-type with an exponent of -1/6. Then it will move to the mixed N-type and ionic, completely ionic. Right there, to the mixed ionic and P-type, eventually hydrogen. Very interesting. In fact, if so we predict that this electrical conductivity based on the dominating G. Based on the electrical conductivity, you can predict the so-called transference number. I don't know whether you have heard about transference number before, but transference number typically it's designated with P sub I. And it's defined as electrical conductivity coming from species I divided by the total conductivity. So take a material like, any oxide, MgO, or any other material. And you measure the total electrical conductivity. And part of that conductivity may come from the motion of magnesium, nitrogen, and iron. Part of it may come from transport of oxygen ion. Part of it may come from electronic type, either electron and or electron hole. I don't know. If I don't know the material, these are all possible. And also, magnesium may be the material that will give electrical conductivity associated with magnesium, oxygen may be moving, give electrical conduction, and then you may get electron and hole in general. In that case, you can see that if you are calculating transference number for O2 minus, for example, it will give you something like conductivity coming from that species fusion divided by the total. So this transference number would be a measure of what percent of the total conductivity is being contributed by that particular species. So let's say for my material I get this to be practically 1. What would that mean? That material is dominated by 100% oxygen ion. In fact, in stabilized zirconia, this is what exactly happens. You can see that given the electrical conductivity, you can if I plot now that oxygen ion transport number as a function of, I think, logarithm of PO2. So at low pH, you can see that it's n-type. So when I have low PO2 n-type, what is the transference number for oxygen ion? It will be 0. Because n-type is all electronic, 100% electron. So this will be 0. If you move into the mixed region now, so now you will have electronic n-type as well as ionic. So your ionic transfer number will keep on rising. And eventually when you move to the flat region, so this is n-type, mixed, ionic, so this will be practically 1. And then on the other side it will go to mixed and to p-type. Why is this important now? If you have, based on the conductivity data, you can predict. Now you can see that this PO2 range is where the material will get purely oxygen ion, that 100% oxygen. And that's the requirement for any electrochemical cell for an electrolyte. If you're creating an electrochemical cell, or oxygen sensor or fuel cell, you use stabilized zirconia membrane. The membrane will have to be 100% pure ionic. And your whole research will tell you what is the range of your where you can maintain that. Very, very useful for us. You know that if you want to use that material as an electrolyte in a device, make sure you do not cross this boundary. Because as soon as you cross, that material will become a mixed ionic electronic conductor. And when you introduce electronic conduction in your electrolyte, you know what happens? The operation of the galvanic cell. You get this so-called leakage current proportional to the fraction of the electronic conduction. So electronic conductivity is 10%, your leakage will be 10%. Your voltage of the galvanic cell will be 10% less. And that's why you need 100% purely ionic conductor. So you can see that this kind of analysis gives you this important regime for operating the device. Good thing about stabilized zirconia is that this PO2 range happens to be huge. It's many, many orders of magnitude. Think about the fuel cell. You know what happens to the fuel cell? If you're using stabilized zirconia, we could talk about this solid oxide fuel cell. In that cell, you will basically have a membrane of stabilized zirconia, either YSZ or calcium stabilized zirconia. So that's your electrolyte. And one side will be, you put strips of platinum for your electrical contact and catalyst. And from one side you'll be flowing air, source of oxygen, and the other side you'll be flowing fuel. Ideal fuel would be hydrogen, obviously. And oxygen will create this O2 minus on this interface, and those O2 minus will move from the right to the left, and this O2 minus will come in contact with the fuel, and it will have a reaction at this interface producing primarily water vapor. And in the process, you will get flow of electron through the external cell. So that's the whole idea of you're converting the energy of the field into electricity, as chemical energy into electricity. But you can see that this material, your electrolyte, will have to be able to withstand both the oxidizing environment as well as reducing environment. How many materials can you name to be able to survive both oxidizing and reducing environment? Very few. Not too many materials. Or YFC happens to be one of them. I think it's still safe, still going to maintain this purely anionic regime in a large approach. So that's the advantage. By the way, in fact, there's a much better oxygen conductor in, I think it's bismuth oxide, I can't remember. Delta bismuth oxide. Delta phase of bismuth oxide is a much better oxygen conductor than stability bonds. But nobody talks about bismuth oxide used in advice. Everybody talks about physical. Do you know why?
Yes.
Like, delta phase of bismuth oxide is stable only the very narrow range. So it's not going to be conditioned. So if you have to take a science application for that, we have a range of, you can use bismuth oxide. But for something like fuel cell or wider range of CO2 applications, that material is no good. So you can see what this phase, program gate diagram is giving. So you can go exercise like this so that from a variant you can see that what the outcome is very important for technological. So don't forget your program gate diagram if you are dealing with this kind of problem. Okay, with that, let's move on and I'll spend a little bit more time and then you have to leave, some of you have to leave easy. So here is something that you can do simply by thermodynamic calculation. So zinc oxide, for example, there is some controversy that at low PO2 is insufficient zinc singly active again. And some experiments indicated, or some researchers indicated singly, some said no double ionized, and there was a controversy. So you can do some thermodynamic calculation. So it's singly active. You can see that this is step number 1, writing the equilibrium reaction, predicting singly ionized zinc infestation compensated by electrons. So in our notation, this will be deeper. But I use the input that uses N or that. This is step number 2. You can see that writing the equilibrium constant of that reaction. This is step number 3, electron neutrality condition. So use this electron neutrality condition in the air and solve, eliminate one of these and solve for the, the defect concentration, and it comes out to be PO2 to the negative 1,4. Now, if you measure electrical conductivity of the zinc oxide as a function of PO2, you see that electrical conductivity should have the same dependence, because conductivity is going to come from these electrons. And if the electron concentration is varying in this manner, your conductivity will vary exactly the same. So we measure it from the and can see whether this is correct. The other option is doubly ionized. You can see this is doubly ionized. Step 1, step 2, step 3, electrochemical segregation, and the solution. It's now CO2 the negative oxygen. So let's go and do the method and see whether it's negative 1/4 or negative 6. Giving negative 1/4. And you are having here some of it can solve this controversy. The simple from the next calculation. And tell the explanatory effect. So this is correct. It's in here. With that, move into the stop here. You can, what do you think? Continue with us in the next lecture or okay, money? How many lectures will be next? Or next week, right? Yes. I think I can probably stop here and still finish on time. All right, have a good weekend, I guess. I'll see you on Saturday. We keep your odds and problems. But that's it.